Today we are going to do two examples of exponential growth and decay, which are differential equations that have the form dy dt equals k times y, with an initial condition y of 0 equals some value y sub 0. And earlier we saw that the solution to these equations were y of t equals y0 e to the k t. We'll start with the concentration of a drug in a person, C of t, which decreases at a rate proportional to the current concentration of that drug, and the constant of proportionality is k equals negative 0.12. So the rate of decrease, dc dt, is equal to negative 0.12 times the current concentration, C. At 2 p.m., the concentration is 8 millimoles, so we will make that our initial condition, C of 0, 0 representing 2 p.m., equals 8. The solution to this equation is C of t equals 8, the initial condition, e to the negative 0.12, the constant of proportionality, times t. And this will describe the concentration of the drug over all time. For example, we can find the concentration at 5 p.m., which is 3 hours past 2 p.m. So C of 3 is equal to 8 e to the negative 0.12 times 3. And that is approximately 5.58 millimoles. Then we can find the concentration at 10 p.m., which is 8 hours after 2 p.m. So C of 8 would be 8 e to the negative 0.12 times 8, and that would be approximately 3.06 millimoles. A quantity that's often of interest is how long it will take the concentration of the drug to reach half of its initial value, or half of C0. So we will take the solution, 8 e to the negative 0.12 t, and set that equal to 4, which is half the initial value, and try to find t. So that tells us that e to the negative 0.12 t must equal 1/2 if we divide by 8. We want to isolate t by taking the natural log of both sides. And that leaves us with negative 0.12. T is equal to natural log of 1/2. And that tells us that t is equal to natural log of 1/2 divided by negative 0.12. Using log rules, we can write this as natural log of 2 divided by 0.12. And that's approximately 5.776 hours. So after 5.776 hours, the concentration of the drug has reached half of its initial value, 4 millimoles. In chemistry, we'll call this the half-life. And you can see that the half-life as a time is equal to natural log of 1/2 divided by the constant of proportionality, k. We will also be interested in what happens over long time periods, or as t goes to infinity, and we'll see that with our solution, 8e to the negative 0.12 t, that as t goes to infinity, that exponential decays to 0. So the chemical concentration of this drug will decay to 0 as t goes to infinity. Of course, for any finite time, we would still have a positive concentration of the drug, although possibly very small. I'll now move on to an example of population growth. The population of a bacteria colony grows at a rate proportional to the current population with constant of proportionality k. That says that the rate of growth, dp dt, is equal to k times the current population, p. And the initial population in this case is going to be given by p of 0 equals some value, p sub 0. The solution to this equation, P of t, is again going to equal P sub 0 e to the constant of proportionality k times t. But at this point, we have not determined what the constant of proportionality k is. We would need to do some sort of measurement on the bacteria population. So for example, we could measure that the population of bacteria grows to 5 times its initial value after 2 days, or P of 2 is equal to 5 times P sub 0, and we can use that information to find K. So P of 2 for our solution is P sub 0 e to the K times 2, and we can set that equal to 5 times the initial population, P sub 0. Notice that we can divide by P sub 0, and we just have that e to the 2k is equal to 5. We can isolate k by using a natural log. Natural log of e to the 2k is equal to natural log of 5. And that tells us that 2k equals natural log 5, or that k is equal to 1/2 natural log of 5. And that's approximately 0.8047. So our solution to this differential equation with that extra added information about population growth is P of t equals P sub 0 e to the 1/2 natural log 5 times t, which we could approximately write as P sub 0 e to the 0.8047 t. But I don't suggest using that decimal approximation because it's in the exponential, and therefore the error in that approximation will grow exponentially. So I do suggest using 1/2 natural log 5 when plugging that into your calculator for computations. A quantity of interest that's off in population growth is the doubling time, the time it takes for a population to double in size. And so we can find that by setting our solution to this equation, P sub 0 e to the 1/2 natural log 5 times t equal to twice the population. And again, we'll see that the initial population will cancel. We can isolate t by taking the natural log of both sides. And that will give us that 1/2 natural log 5 times t is equal to the natural log of 2. Okay, so then t must be equal to natural log of 2 over 1/2 natural log of 5. And that's approximately 0.8614 days. So it takes a little less than a day for the bacteria population to double in size. This is called the doubling time. And you can find it by finding t equal to natural log 2 divided by the constant of proportionality k. Now note that for any P sub 0, if we want to look at what happens as t goes to infinity, that we have exponential growth, and so the limit as t goes to infinity of P of t is infinity. And in mathematics we say that that means the population explodes, that it grows exponentially.